All right, we're in section 10.3. All right, so for today, we're going to start with, we're going to talk about slopes and tangent lines. And if we have time, and if I have the energy, we'll come up with the formula for arc length with parametric equations. So slopes and tangent lines. So we have a smooth curve. And it's given by a pair of parametric equations. So x is some function of t, and y is some other function of t. The slope of our curve at some point xy is dy dx and we can say that is dy dt divided by dx dt where dx dt is not 0. So in shorthand we could say this is dy dx equals f prime over g prime. Sorry, I did that upside down, didn't I? G prime over x prime. And the proof of this is very, very straightforward. I'll sketch it out really quickly here. Here's our graph. Here's our curve, like so. And we want the slope at a particular point. So we'll look at the change in x and the change in y. And we'll take the limit as delta t approaches 0. So this is delta x, delta y. We have a point here at f of t and g of t. That's that point. And up here our point is f of t plus delta t and g of t plus delta t. So delta x is just going to be f of t plus delta t minus f of t. Delta y is going to be g of t plus delta t minus g of t. And as delta x approaches 0, delta t is approaching 0. So our slope, if we're looking at the limit as delta t approaches 0 for our slope of g of t plus delta t minus g of t, and we're dividing by the change in x, f of t plus delta t minus f of t. We have to get our delta t in there somehow so we can take our limit. So we just divide the numerator and denominator by delta t. So this is the limit as delta t approaches 0 of our same quantities, t plus delta t minus g of t divided by delta t. And that is in our numerator and our denominator. We just have the same, these quantities with f, and we're dividing that by delta t. And as delta t approaches 0, this is just f prime over g prime. Or, sorry, g prime over f prime. I do it again. G prime over f prime. And we, just to make sure we know we're talking about a function in t, I'll put our t's in there. So this is how we find the slope of a curve represented by parametric equations. We can use this process repeatedly. Now, higher derivatives, it's kind of interesting, the pattern that develops. That we can use this process repeatedly to find higher derivatives. So, any questions on this before I switch the page? Pretty straightforward. Look at how we find the slope. All right, so we repeat the process. For higher derivatives. So if we want the second derivative of y with respect to x, this is the derivative with respect to x of dy dx. And using the process that we just used, now our function is dy dx. And we're taking the derivative of that, so that function is going to be d dt of dy dx divided by dx dt. So we take the derivative with respect to time of our derivative of dy dx, and we divide it by dy dt. So dy dx is our new function, and we repeat the process that we just talked about. If we want the third derivative, this is the derivative with respect to x of the second derivative. And by the process we used previously, this is the derivative with respect to time of the second derivative of y with respect to x divided by dx dt. So we're taking on each successive derivative, we take the derivative with respect to time of the previous derivative of y with respect to x, but each time we divide by the derivative of x with respect to t. So our derivative becomes our new function, and each successive derivative always has this dx dt in the denominator. That make sense? All right. So if we want to, let's do a quick example of finding a couple of derivatives where we could find the slope of a function, and maybe we're interested in the concavity. So we're going to calculate a couple of derivatives. So we have x equals 5 cosine t and y equals 4 sine t for 0 less than t less than 3. We want the slope and concavity at 5 square root of 3 over 2, comma 2. So we're interested in the slope and the concavity at this point. First of all, what would the graph of these this parametric equations look like? What would it be? It is an ellipse. Yes. Right. So our major axis would be horizontal, right? Minor axis would be vertical. So this is an ellipse. It's good practice to start recognizing what these would look like as we work with them more. So we want to find the slope. Slope is dy dx. And we said that is dy dt over dx dt. All right, so dy dt is going to be what? 4 cosine t, and dx dt, negative 5 sine t. And so we end up with negative 4/5 cotangent of t. And at the point, at this point, what do we need here to find our slope? This is our point x and y. We have to figure out t to find our slope. At 5 square root 3 over 2, I'll just use the x coordinate. 5 cosine 5 square root of 3 over 2. And that is the same as the cosine of, you see what I did here, 5. Oh, I'm sorry. I'm not taking the cosine of 5 cosine t equals, there we go, 5 square root of 3 over 2. All right, so cosine t equals square root of 3 over 2. So t equals what? Pi 6, right. There we go. So we know that t equals pi 6. So dy dx, plug in t equals pi 6 here, minus 4/5 the cotangent of pi over 6, which gives me negative 4 square root of 3 over 5. Cotangent of pi 6 is square root of 3. So my slope at point 5 square root of 3 over 2 is negative 4 square root of 3 over 5. So our slope is negative. Our second derivative for our concavity, we need d squared y dx squared is going to be d dt, the derivative with respect to t, of our first derivative here with respect to t, or with respect to x dy dx, so that's going to be dy dt of minus 4/5 cotangent t divided by dy dx. I'm sorry, but divided by dx dt, divided by minus 5 sine t. And the derivative with respect to t of cotangent, cosecant, negative cosecant, squared. There we go. We finally got it. So we end up with 4/5 cosecant squared t divided by negative 5 sine t. The derivative of cotangent is negative cosecant squared, so the negatives go away. So we end up with negative 4/25 cosecant cubed of t. And we know that t equals pi over 6. At t equals pi over 6, this equals our second derivative. Finally, we plug that in and we get negative 32/25. Cosecant of pi over 6 is 2. So now we have our slope and our concavity. So our slope is negative, our concavity is negative as well at that point. So finding slopes, finding derivatives for parametrics involves a little bit of plugging and chugging in these types of problems. Any questions on that? Now something interesting happens with parametric equations, because y is not necessarily a function of x. So parametric equations can curves for the representations of parametric equations can cross each other, and where they cross each other, they can have more than one tangent line. So an example, we talked about it a little bit yesterday. We showed the video of it. Is a prolate cycloid. So let me grab a prolate cycloid here. I have a nice graph of one. So this is the graph. The circle, a point on the circumference of a circle rolling, or not on the circumference of the circle, the point beyond the circumference of a circle rolling on a straight line. So the example, we said it was like a train wheel. It goes below the train track at one point. So this is our prolate cycloid. So let me grab a picture of that. Put that in the page. So there's my prolate cycloid, and the equation we said was for this, x equals 2t minus pi sine t, and y equals 2t minus pi cosine t. So we can see here at the point 0, 2, we can have two tangent lines. Where it crosses over there, we have two tangent lines. So let's find the slope of those two tangent lines using our parametric equations here for a prolate cycloid. So dy dx, our slope, equals dy dt over dx dt. So we end up with pi sine t over 2 minus pi cosine t. Did I write my equations incorrectly? Y should be, this is just 2. Sorry. That's just a 2. The t is not in the equation for y. So our slope, and we're looking at the point 0, 2. That corresponds to t is pi over 2. Or at the point 0, 2, we end up with t equals plus or minus pi over 2. So we end up with two slopes here. We have dy dx equals pi over 2 or negative pi over 2. So if we're rolling along here, we hit this point at t equals pi over 2, and then we continue around, or negative pi over 2, we continue around, and it's we hit this point again at pi over 2. And our slopes turn out to be pi over 2 or negative pi over 2. So we have two tangent lines. One has a slope of positive pi over 2, this one here, and one has a slope of negative pi over 2. And our tangent lines, if we use our point slope form, we end up with our tangent lines of y minus 2 equals pi over 2x, and y minus 2 equals minus pi over 2x. We can have two tangent lines where our curve crosses each other. So that's an interesting thing that happens with parametric equations. Because they don't necessarily represent functions, we can have multiple tangent lines at the points where they cross. Questions on that one? These curves, the prolate cycloid, and all the different curves that come from circles rolling on other shapes, I find them pretty fascinating. All right, the other thing we're interested in when we talk about parametric equations is when our tangent lines are vertical and horizontal. So we want to figure out when our tangent lines are vertical and horizontal. So we have parametric equations for x equals some function of t, just like before, and y equals some other function g of t. If dy dt equals 0, and dx dt does not equal 0, what kind of tangent line do you think that's going to give us? This is going to give us a horizontal tangent line. So we're not going, our curve, our derivative is not increasing in the vertical direction, and the derivative in the horizontal direction is not 0. This gives us a horizontal tangent line. And we'll switch the conditions around for our vertical tangent line. If dx dt equals 0 and dy dt not equal 0, we have a vertical tangent line. And when I think of these, I always think of them kind of physically. If dy dt is not 0, or if dy dt is 0, we're not going up and down, and dx dt is not 0, so we're going side to side. So we're not going up and down, but we're going side to side, so we have to have a horizontal tangent line. And if dx dt is 0, we're not going side to side, and dy dt is not 0, so we have to be going up and down, so we have a vertical tangent line. That's how I remember how I keep these two straight. So these are the conditions for our vertical and horizontal tangent line. Questions on that? All right, so we have a choice now. We can go through, I can derive the equation for arc length. We don't need it today, but if we don't derive it today, then we'll have a lot to do on Monday. So would you rather do it now, or would you rather wait till Monday? Who would rather do it now? Just have a little time now. Who would rather do it Monday? Oh, we have a tie. So, Ahmed, what do you think? And either way, okay. So, should we come up with a formula for arc length today, since we have almost a half an hour left? Or if we wait till Monday, then we're going to have a ton of stuff to do on Monday. You don't know?
All right, today.
Today? Okay. Ahmed says today. All right. It's not long, and it works off of something that we've done before. All right. So otherwise, we just end up with a whole bunch of stuff that we have to do on a short day on Monday. So this is what our homework tonight is. Just talks about finding slope, finding concavity, finding vertical and horizontal tangent lines. So just taking derivatives. The next thing that we're going to do is arc length. So I just wanted to come up with a formula. So we can use it on Monday. All right, so remember that for when we have y equals a function of x, and I'll call it, I want to use f or something else. So if y equals h of x, the arc length our arc length formula is s equals the integral from, I'll just say a to b, of 1, the square root of 1 plus h prime squared dx. And I'll just rewrite this just because, so it's in a notation that we're going to use for our parametric equations. 1 plus dh, or dy dx squared dx. So that's our arc length formula if y equals some function of x. And here we said our function was h. Well, now we're going to take our expression for the derivative dy dx with parametric equations. So we're going to say if we have x equals some function of t, f of t, and y equals some other function of t, we'll call g. And we're integrating from t equals a so here a and b were our limits on x. Here we're going to let a and b be our limits on t. We can write that s equals the integral from a to b. We had an expression for dy dx with parametric in terms of our parametric equations. This is going to be the square root of 1 plus dy dt over dx dt squared dx. That was our expression for dy dx when we have parametric equations. But we want to write this all in terms of t. So I'm going to say that dx is dx dt times dt. And we'll rewrite this all in terms of t. That's the whole point of what we're doing here, is to rewrite this expression in terms of t. All right, so we're going to say that s, oops, that's not what I want to do this. S equals, our arc length, it's going to be the integral from a to b of, I'm going to, first I'm from this expression, I'm going to use dx dt squared as my common denominator and write this all in terms of a common denominator. So I'm rewriting this expression with dx dt squared as the common denominator. So when I rewrite that, I end up with this big radical dx dt squared plus dy dt squared all over dx dt squared. And let's make sure we know that our radical includes the dx dt. And outside here, for dx, I'm going to say this is dx dt times dt. Does anybody see what I'm going to do here? Nice little algebra trick that I'm going to do.
Take the square root of the bottom.
Take the square root of the bottom, and that would just be 1 over dx dt. Or I could square the dx dt and put it inside the radical. Either one's the same thing, right? So I can take the square root of this dx dt squared, and then I end up with just 1 over dx dt, and it's going to cancel with this dx dt out here. So my arc length turns out to be just the square root of dx dt squared plus dy dt squared times dt. And if we want to write this just in a little more concise notation, it's going to be the integral from a to b of the square root of f prime of t squared plus g prime of t squared. dt. And this is the arc length for a curve on our interval from a to b, where our curve is represented by x equals f of t and y equals g of t. And the important thing about finding this arc length, our curve can't intersect itself except at the endpoints. So we can find the arc length of a closed curve, but the prolate cycloid, let me go back to our little graph here. We couldn't use this formula to find the arc length from here, say, to here, for example. We'd have to break that into several intervals. So we can find the arc length for the loop, and then we can add the arc lengths for these two pieces. So we have to be sure that our curve doesn't intersect itself except at the endpoints of our interval. So that's the one thing we have to be careful with when we use this arc length. And we'll talk more about that on Monday. So that was relatively painless, right?
Yeah.
All right.
If you want to do that.
Right. So don't you feel better, Juliana? Didn't that give you a huge sense of relief?
Didn't you feel more excited about the weekend?
Right.
So let me get the first one. Not to do this. We're trying.
All right. All right, there's your homework.